So our first talk of the day is by Andrea Sangiovanni, who will tell us about open string methods and Gopakumar-Vafa invariants. Take it away, Andrea.
Thank you. So I'm Andrea Sangiovanni from the University of Trieste. And as a first, I would like to thank the organizers for giving me the opportunity of being here. Today, I'll talk about open string methods and Gopakumar-Vafa invariants, basing myself on work in collaboration with Andres Collinucci from Bruxelles, Roberto Valandro, my supervisor from Trieste, and Mario De Marco from SISSA, also in Trieste. The overarching theme of this talk will be the close relationship between stringing methods and topological invariants. The punchline will be that we can get insight and concretely handle computations of physically relevant mathematical objects, such as topological invariants, by using string theory techniques. That's also getting information about the physical origin of such objects. The outline will be the following. I'll first explain what exactly are these Gopakumar-Vafa invariants, known as GV invariants. Then I'll go through why we are interested in counting them. That's the motivation for this talk. And the main part will be devoted to explaining a new idea to find an easy and physics-based way of computing the so-called genus zero GV invariants for a class of non-toric Calabi-Yaus. And the strategy to do this, we rely on the M-theory and type 2A duality to reduce the problem to a more familiar setting. And then, using the tachyon condensation formalism, I'll show how we can compute the open string spectrum. And finally, I'll make an identification between the open string spectrum and the GV invariants of the Calabi-Yaus. So let me get started from the first part. So what are these GV invariants? They are a class of topological invariants, and topological invariants are objects that do not change under homeomorphisms. So the most trivial example one can think of topological invariants is the genus, which, roughly speaking, counts, for example, holes in a Riemann surface. But actually, for applications in string theory, we are interested in topological invariants of Calabi-Yau manifolds, and that's what GV invariants are. So just to give you a rough mathematical definition of GV invariant with no claim for precision, we can consider the following. A Riemann surface, sigma G, of some genus G, a Calabi-Yau threefold, S3, meaning that it is 3 complex dimensional, and a 2-cycle beta inside this Calabi-Yau, belonging to this homology class. The question now is, how many of these holomorphic maps can we build from the Riemann surface sigma G to the 2-cycle beta inside the Calabi-Yau X3? It turns out that these maps are counted by the topological invariants called Gromov-Witten invariants that in turn are related to the so-called GV invariants, the Gopakumar-Vafa invariants that we denote with the symbol n beta G, where this beta is the 2-cycle inside the Calabi-Yau and G is the genus of the Riemann surface. So the GV invariants, these topological invariants, will be our main objects of interest for the rest of the talk. And more specifically, I'll focus on genus 0 GV invariants and beta 0, meaning that the Riemann surface in that case is just a sphere. The question now is, why do we care about this kind of invariants? What are they useful for? The main point is that m beta G gives the number of BPS states of M2 branes that wrap the curve beta inside the Calabi-Yau. And furthermore, we can say that Ng of a multiple of the class beta, so of D beta, counts bound states of D M2 branes wrapping the same class beta. Just to give you an example of a concrete application, we have that m beta 0 gives instantonic corrections to the Kähler potential in type 2 theories, where we have the usual perturbative contribution due to the moduli plus some instanton correction that depends on the GV invariants. So that's one of the reasons why we want to characterize GV invariants for Calabi-Yau manifolds. The point now is, how can we do this? How can we compute in practice the GV invariants? We know that for toric Calabi-Yau threefolds, so for the toric case, there are existing techniques, for example, the topological vertex, and also for some non-toric cases, there are available methods due to these authors, Katz, Donovan, Weems, Toda, and many others. And in the following, I'll focus on this latter case, so on non-toric cases. Specifically, I'll be interested in singular non-toric Calabi-Yau threefolds that arise as one-parameter families of deformations of ADE singularities. So this was a long string of words, so I'll go through each part in order to exactly understand what's going on. The crucial fact is that this kind of threefolds that we consider often admit a C-star fibration with or without oriented folding, and this fact will be very important in tackling the problem of computing their GV invariance. This will be the fact that allows us to perform the computation. Now, let me explain what these ADE singularities are. ADE surfaces, just briefly, ADE surfaces are singular spaces classified in terms of the exceptional divisors in their resolution. So for example, if we take the AN case defined by this equation, we have that it is singular, we can see that it is singular at the origin, and that we can resolve the singular point and obtain a chain of n p1s arranged, as you can see here on the right. Analogously, for the Dn case, which has this different equation, we have a different pattern of p1s that arise from the resolution of the singular point at the origin. In the following, I'll actually consider singular threefolds where only one of these p1s can be blown up, and these are called simple flops. And here also I have shown you twofolds because we have three variables and only one equation, but we want threefolds. The point is that we can make a threefold out of an ADE surface by deforming it with terms that depend on a single parameter W. So just to give you an example, if we have an A1 singularity, we can add some deformation term depending on a complex parameter W, and now we obtain a threefold. In this case, we see that this family is not singular because the term depending on W is linear, but taking into account wild theory, we can see that it dictates how we can choose the deformation parameters in order to achieve a singularity and a specific resolution pattern. So the famous example of the conifold is just an A1 singularity with a deformation that now is quadratic in this complex parameter W. And we see then that it is singular at the origin and that there is a single P1 that can be blown up. Now, consider M theory placed on top of one of these singular threefolds that arise from ADE deformations. Then Witten has taught us that the effective theory in 5 dimensions that comes from dimensional reduction of the 11-dimensional M theory contains hypermultiplets that descend from the M2 branes that wrap the holomorphic curves in the Calabi-Yau. And the states of the hypermultiplets that live in the 5-dimensional theory are exactly the objects that we want to study. These are the states that we want to count because we will see that they are in one-to-one correspondence with the GV invariance of the Calabi-Yau manifold of the threefold that we have here. Now, how can we do this? How can we achieve this result? First, I have to use a trick. So we write the threefold in the form of a C-star fibration. So in this shape, UV equals determinant of some matrix T that I'll define in a second, where the C-star action is on the first two coordinates, U and V, in this shape you see here. Furthermore, the S1 in this C-star action is the M-theory circle. And to give you an example of this rewriting, we can take always the conifold, where just by changing variables from X and Y, we get to U and V and obtain the desired form. The relationship then is the following. We have M theory placed on top of this threefold, UV equals determinant of this matrix T. And by reducing on the M theory circle, we obtain type 2A with D6-branes that live on the locus determinant of T equals to 0, where this locus determinant of T equals to 0 is where the C-star fiber degenerates. In the following, I'll be interested on the right-hand side of the story. So on type 2A theory and D6-branes, we will consider strings stretching between the D6-branes on this locus. The question that is left to address is, what is this matrix T that I've introduced? The answer comes from the tachyon condensation formalism, first developed by Sen in 1999, that roughly speaking says the following. We can consider a stack of D8-branes and a stack of anti-D8-branes connected by some tachyonic strings that can be arranged in a tachyon matrix. Physically, this means that the tachyonic strings signal the fact that the system is unstable. And so what happens is that the D8 and anti-D8 brane stacks collide and annihilate. If the tachyonic matrix is of some specific form, there can be some D6-branes left over after the annihilation, as you can see here on the right. And mathematically, this is formalized by saying that the tachyon matrix T is a map between two vector bundles, E and E tilde, that belong to the D8 and anti-D8 stack. And the locus where the D6-branes appear is given by the co-kernel of the tachyon matrix T, where the co-kernel is just defined as the quotient of the vector bundle E, where the map ends, mod the image of the map itself. And mathematically, this is a sheaf that is localized on the locus determinant of T equals to 0. So we see that the tachyon condensation formalism gives us a way of describing a setup of D6-branes that we like by choosing an exact tachyon that we must find. So just to, in addition, this tachyon is subject to the gauge symmetry that comes from the D8 and anti-D8 brane stacks. And the action of this gauge symmetry on the tachyon is as you can see here, where the matrices G and G minus 1 belong to the gauge group of the D8 and anti-D8 brane stacks. Our objective now is to compute the open string states in the D6-brane system that is left over after the D8 and anti-D8 partial annihilation. And we will do this by considering fluctuations of the tachyon, delta phi, that are formalized by these vertical maps between these two complexes where the tachyon acts. So the maps delta phi will be in correspondence with the open string states. And in order to perform the computation, we will have to mod them by the gauge symmetry that acts on the tachyon. This means that we have to consider this diagram that is obeyed by the fluctuations of the tachyon delta phi. And in the Lie algebra, this implies that the equivalence relation satisfied by the fluctuations is as follows here. So delta phi will depend on the gauge symmetry G D8 and G anti-D8 and the tachyon matrix itself, T. So just to give you a recap of what I've shown you so far, the strategy to compute the GV invariants is as follows. We consider Calabi-Yau threefolds defined as one parameter families of ADE deformations. This is our setting. Then we use the M-theory and type 2A duality to give a description of the corresponding D6-brane system, and we build the tachyon that describes this D6-brane system. Then we compute the fluctuations of this tachyon that correspond to the open string modes, and finally we identify the open string modes between the D6-branes with the GV invariants of the Calabi-Yaus that we started from. So let's see how this works in concrete and explicit examples. The first actually is a known example. So consider a stack of n D8-branes and n anti-D8-branes, and a tachyon matrix which is just the identity matrix. In this case, we see that trivially the co-kernel of T is equal to 0. And so physically, this means that there is a total annihilation between the D8 and anti-D8 brane stacks, giving nothing left. There are no D6-branes left over, and so there's nothing to compute. Now, getting to a more interesting example, we can consider Reed's pagodas. Reed's pagodas are a natural generalization of the conifold, and they can be described by deformation of an A2k-1 singularity fibered over some complex plane spanned by W. So we have here an A2k-1 singularity plus a quadratic term depending on W. It can be shown that this geometry is singular at the origin, and that it admits a single P1 in the resolution, which is the central P1 of the A2k-1 chain, where here I've depicted the lowest k case with k equals to 2. So we have an A3 singularity where only the central node can be resolved. What we want to do now is to describe this geometry as a C-star fibration. So just as we did for the conifold, we rewrite it, changing variables from x and y and going to u and v. And on the right, I've just factorized what we had above. Then the last step is to find the tachyon, that is a matrix T in the algebra of A2k-1 or one of its subalgebras, such that its determinant is equal to the right-hand side of this equation, of the product of these two vectors. So in order to do this, consider a stack of two D8 branes and two anti-D8 branes. The tachyon will then be a map in this exact sequence where there is the structure sheaf here and the cokernel of T here. It turns out that the minimal tachyon that does the work of reproducing what the D6-brane setup that we want is this one depicted here, because trivially its determinant reproduces what we expected. Physically, what we are describing is a system of two branes, each one corresponding to one of these factors, that intersect each other on a single point defined by z to the k equals to w equals to 0. And what we want to do now is to compute the open string modes that stretch from one brane to the other near the intersection point. In order to do this, we have to consider the fluctuations delta phi of the tachyon and mod them by the gauge equivalences, where now these matrices G D8 and G anti-D8 belong to the algebra SL2 plus SL2. Doing this, we see that there is a choice of these matrices that preserves the tachyon, and it is given by this diagonal matrix G minus G that is just a U1 inside this algebra SL2 plus SL2. Now, putting this aside, so not considering the choice that preserves the tachyon, we are left over with the actual transformation that we must gauge from the fluctuations of the tachyon. So in practice, what I'm saying is that we have to consider this usual relation with some explicit choice of the matrices GD8 and G anti-D8, where we have put away the overall U1 that I've shown you before. Performing the explicit computation, we find that delta phi satisfies this equation. So delta phi will be equivalent to itself, where I've just rewritten it in a convenient way, plus something that depends on the blue entries, which are just the coordinates z and w on the branes, and the gauge parameters g, a, and b. What we want to understand now is if there is any localized fluctuation near the intersection point. And in order to see if there is any, we can at first consider, for example, the mode delta phi 0, which is this diagonal one. And we see that gauging with choosing the gauge parameter g in an appropriate way, we can eliminate all the dependence of delta phi 0 on the combination z to the k plus or minus w. This implies that delta phi 0 is localized on the ideal z to the k plus or minus w, and so it is spread all over one of the branes, and as a result, it is not dynamical in 5 dimensions. On the other hand, we have the delta phi plus, by considering the gauge symmetry given by A and B, can be localized on the ideal z to the k and w, which is just the intersection point between the two branes. This means that delta phi plus gives rise to k modes that stretch from one brane to the other near the intersection point. And in the same way, delta phi minus gives another k modes stretching from one brane to the other. Summing up, what we find is that there is a total of 2 k modes, each corresponding, in total corresponding to k hypermultiples in 5 dimensions. And on the other hand, the GV invariants for this kind of geometry, so for the Ritz pagodas, are as follows. We have that N0 of genus 0 refer to the class of the exceptional P1 of the Ritz pagodas is equal to k, and all the other GV invariants vanish. And so we see that there is a perfect agreement between the number of hypermultiples in the 5-dimensional theory and the GV invariance of the geometry. And this was the result that we wanted to find. We wanted to make this correspondence between physics and geometry. I should also notice at this point that all these hypers in 5D have the same charge with respect to the U1 that commutes with the tachyon. They all have, let's say, charge 1. Now, let me show you a slightly different example that has some subtleties, which is the example of Laufer's flop. This arises as a deformation of a D2k plus 3 singularity with this equation that you can see here. And we can see again that this geometry is singular and that it admits a single P1 in the resolution, corresponding to the central node of the DN Dynkin diagram. As you can see here on the right, this is just the D4 case, which arises from as a deformation of the D5 singularity. What we want to do now in order to compute the GV invariance of this geometry is to first rewrite this equation as a C star fibration. But with respect to the Ritz-Pagola's case, there is a subtlety, because in order to realize this geometry in type 2a, we have to introduce a non-6- plane along with the D6-branes. And this non-6- plane induces an orientable action that changes the sign of this coordinate xi that goes minus xi, where xi is related to the coordinate z that was in this equation here above by this relation. Now, having done this, which is the main difference with respect to the previous case, to the case of Ritz-Pagodas, we can rewrite this geometry as a C star fibration, and we find that the locus where this C star fibration degenerates is given by the determinant of the tachyon matrix, and it is the locus of the D6-branes, and it is given by this equation. Physically, what we are describing is a brane, for example, this one given in the parentheses, and its image brane, this other one, because we see that the sign of the xi entry changes due to the orientable projection, plus some other branes represented by this vector. The tachyon that reproduces this determinant is a map in the exact sequence that you see here, where again we have the structure sheaf, and explicitly it reads, as you can see here at the bottom. Now, there is a slight difference with respect to the case that we have seen before, because we have to consider the fluctuations of the tachyon in order to compute the open string modes, but we have to mod it by some different relation as respect to the before, as explained by Colinucci, Denef, and Ezolet. And so the relationship that is satisfied by the fluctuations of the tachyon delta phi is depicted here, where G is a matrix in the Lie algebra of the D8 and anti-D8 brane stacks, and sigma star is the pullback of the involution that changes sign from xi to minus xi. Taking this fact into account, we find again that there is a U1 that commutes with the tachyon given by this diagonal choice. Now, performing the explicit computations with the gauge symmetries that are left after picking out the U1, we find that there are 2k plus 3 hypers of charge 1 with respect to that U1 localized near the intersection point between the branes. And there are also k hypers of charge 2 with respect to the U1. On the other hand, we see, as for example computed by Toda, that the GV invariants for this geometry are as follows. We have that N0 referred to the class of the exceptional P1, so the central node of the Dn series, is equal to 2k plus 3, and that N0 of twice the class of the exceptional P1 is equal to k. And so again, we see that there is a perfect agreement between the number of hypermultiplets and the GV invariants for the geometry. We have obtained also analogous agreeing results for other cases in the Dn series. For example, the examples examined by Brown and Weems in one of their recent papers. As a last brief example, let me show you the case of non-resolvable singularities. These are ADE fibrations that do not admit any Kähler resolution. So for example, if we take an A2 singularity and we deform it with some term depending on W squared, we see again that it is singular at the origin, but this time there is no P1 that can be resolved. And the question now is, can we say something about such cases? Does our technique work in some way? And the answer seems to be in the positive, because we can explicitly build a tachyon that reproduces the D6-brane setup that corresponds to this geometry. And by performing explicit computations, we find that there is one uncharged hyper near the origin of the space and nothing else. And this can be seen also from many other similar examples. The moral in this case seems to be the following. If you can build a tachyon that describes the D6-brane setup, then you can also compute the open string spectrum near the intersection point, and as a result, also the genus 0 GV invariants. I should also notice at this point that for higher degree cases, we can choose different tachyons depending on the T-brane choice that we make, giving rise to different spectrum for each choice. And this will be an interesting avenue for the future. So summing up, what I've told you so far is that we have seen that the tachyon is a multi-purpose tool, like a Swiss Army knife, that allows us to compute open string states between the 6 branes, and so GV invariants for the corresponding geometry. It allows us also to find the preserved gauge group after taking condensation, and in this way to investigate the structure of the Higgs branch of the 5-dimensional theory, thus also detecting discrete groups that act on the moduli space of the 5-dimensional theory. And this fact is crucial in allowing us to check with the existing results, for example, the ones presented in this very recent paper by Colset, Schaffer-Lameki, and Wang. And finally, the tachyon is also a useful tool to detect the flavor group of the 5D theories where the hypermultiplets sit. So in conclusion, what I've tried to tell you today is that there is a physics-based way to compute genus 0 GB invariants for a wide class of non-toric Calabi-Yaus, and that this technique applies both in orientifold and non-orientifold D6-brane setups, so for the AN series and the DN series, and that this method also furnishes information about non-resolvable singularities, which were inaccessible to other techniques. So for the future, we are thinking about considering multiple flop singularities, because as of now, we have just considered the so-called generalized conifold that admits 2 P1s in the resolution, but that's our only example for now. And then we also consider switching on T-brane energies in the tachyon in order to better understand the hierarchy in the spectrum of the modes. And finally, we will apply this technique to other more involved single flop and non-resolvable singularities, thus allowing to connect with existing and future literature. So this will be everything from me. Thank you very much.
Okay, thank you very much, Andrea, for the very nice talk. Let us all thank Andrea with our emoji of choice. Let me ask the first question. Yunan has a question. Yunan, you can go ahead, then I'll ask mine.
Hi. Can you hear me? No?
Yeah.
Oh, yes? Okay,
yep.
Good. So I just wonder whether you can apply this new method to non-isolated singularities, because in all your examples, I think the singularities are isolated. Okay.
Yes, that's a good question. For now, we have not tried to do it, but let's say that we should see if we can. The crucial point is that if we can rewrite the geometry in the shape of a C-star vibration, and if this is possible, it could be plausible to try and investigate this avenue in order to see if there is a way to compute the open string states, because I suspect that there could be some difficulties given by the fact that there's a curve of singularities, and so we do not have maybe localized modes. But that's surely an interesting perspective to consider.
Okay.
Okay, next question is from Federico.
Hello, very nice talk, thank you. So I have a curiosity. If you compactify type 2b on this RAID pagodas, you get a class of 4-dimensional Argyres-Douglas theories called A1, A2k-1. And for these theories, the necklace of partition function is not known up to date. So natural question would be if you could say anything about the Gopakumar-Vafa invariants of the mirrors of the RAID pagodas. Is something known about them, or can you use these techniques?
I should say that we have not thought about this for now, but let's say that, let me just find the slide. Yeah, so what we have done is to compute the GB invariants for the geometries that can be reduced to 5 dimensions. And in this paper by Colset, Schaffer-Lameki, and Wang, they consider also the mirrors, the mirrors in type 2b, where let's say they try to relate the two geometries, so the type 2b perspective and the M theory perspective, seeing the spectrum and the gauge groups. So what we have obtained is a 5-dimensional result, but I suspect that maybe using the techniques explained in this paper, there is a hope of relating these results to type 2b. So this is not a thing that we have considered so far, but I assume that by exploiting this duality, there's a possibility of investigating this kind of thing. I don't know if I replied to your question.
Yeah, I was just curious about the status of the mirror of this class of manifolds.
Yeah. The point is that let's say explicitly, I don't know. Let's say I don't know what to tell you because we have not tried to compute it explicitly. So I would say that maybe if we consider this kind of duality, we could say something perhaps. So this will be an interesting thing to examine.
Okay, thank you.
Thank you.
All right, and let's see. So, Kumran says for the mirror, there's a discussion going on in the chat. Andrea, I think this was probably somewhat implicit in your techniques, but my question is, is there a clean statement for which curves this technique should work for? Is it completely general, or
which curves you mean in the resolution of the singularity?
Yeah. Just if you have a Calabi-Yau threefold, then which curves can you apply your techniques to compute the GB invariance?
Yeah, let's say that a crucial fact that I've not mentioned was that this kind of description, so the fact that we have hypermultiples in 5 dimensions comes from the fact that we have a rigid P1 in the resolution of the geometry. And so this was one of the crucial facts. But as I've shown you in the end, there are also cases that are non-resolvable, so as this one, that have a so-called terminal singularity, so no P1 can be resolved. So the technique seems to be quite general. Let's say it seems to be applicable to many cases, but we have not, as far as I know, we have not a complete and thorough definition of which cases it can be applied to. Actually, we're working on applying it to other non-resolvable singularities and other simple and multiple flop singularities in order to see if it works or if it doesn't. Because for now, we have seen that, for example, comparing with some results by Closet et al., our first attempts in reproducing some other results are, let's say, have to be tuned because there are some ambiguities. And so we are still working on generalizing this kind of technique.
Got it. Okay. Thank you.
Thank you.
Okay. If there are no further questions, let us thank Andrea again.